The first example of two-dimensional motion that we're going to study is what's called projectile motion. Projectile motion is essentially free fall where an object is also moving horizontally at the same time. It will have the same acceleration as free fall because in the air, gravity is accelerating it downwards at 9.8 meters per second squared, but there is no horizontal acceleration. Let's look at it in this example here. In this case, what we have is a ball that rolls horizontally off a cliff. We're going to follow the same steps as we have been before to solve these types of problems, and so let's start by drawing a picture. In this case, I just draw the cliff, and then I draw the ball, and I draw a little bit of motion here to show that it's going off horizontally. I now need to assign it an origin and a coordinate system, and in this case, I'm going to have the origin be at the top of the cliff, and I'm going to have my x direction point to the right, and my y direction point upwards. I now need to write down the kinematic variables, but there will be 3 kinematic variables in the x direction as well as 3 kinematic variables in the y direction. And so we'll need to know a, v naught, and x naught in the x direction, and we'll also need to know a, v naught, and y naught in the y direction. Let's look at the x direction first. The acceleration in the x direction is 0 meters per second squared. It's not accelerating in the horizontal direction. Its initial velocity is 6 meters per second, and we know that it's positive because it's to the right, and we also know that it's 6 because the ball was said to roll off horizontally. The initial position in the x direction is 0 because it was originally located at the origin. In the y direction, the acceleration is negative 9.8 meters per second squared. Again, it's negative because the y direction points upwards and the ball is accelerating downwards. The initial velocity in the y direction is 0 meters per second. This is because the ball is rolling horizontally, so it has no vertical component. The initial y position is 0 meters because it was originally located at the origin. So let's look at part A. Part A is asking how long does it take to hit the ground? In this case, we can rephrase that math question as what is t when y equals negative 5? Again, it's negative 5 because the base of the cliff is 5 meters below and the positive direction is upwards, so that is a position of negative 5 meters. We now set up our kinematic equation, and in this case, the most appropriate equation to use is the first kinematic equation because we're given position and we're solving for time. We set that equation up. We fill in our information, we simplify, and ultimately we can arrive at the answer. It takes 1.0 seconds to hit the ground. Now, there may be some issues with rounding here, and so if your answers are slightly different than mine, if you do it in the calculator, that's fine. That happens because of how many decimal places you choose to round to at the end. In part B, we're asked how far from the base of the cliff does the ball land? And this is a horizontal problem. It's asking us what is x when t equals 1.0 seconds? Why is that the correct question? Because we're trying to find the horizontal distance when it hits the ground, and we know it hits the ground after 1.0 seconds. That's what we found in part A. So here we're trying to find position and we're given time, so the first kinematic equation is the appropriate one to use. We write it down, fill in our information, and solve. In this case, it lands 6 meters from the base of the cliff. Part C is asking us how fast is it traveling when it hits the ground? And this will be a good example of what I talked about in the last chapter about combining vector components together to find an answer. Because what we're really being asked for is what is the speed when it hits the ground? And as you can recall from before, speed is just the magnitude of the velocity. So we're being asked what is the magnitude of the velocity when t equals 1.0 seconds? This will require us to find the velocity in both the x and the y direction. Let's look at the x direction first. In this case, we're going to use the second kinematic equation. We plug our information in from the x direction in our x kinematic variables, and we see that the velocity is 6 meters per second. That makes sense because we know it's not accelerating in the x direction, so its velocity should stay the same. In the y direction, we write down the equation, we fill in our information, and we find that it's moving negative 9.8 meters per second. And again, the negative sign makes sense. It is moving vertically downwards. To find the magnitude, we apply the Pythagorean theorem. The square root of 6 squared plus the square root of negative 9.8 squared. And this is equal to 11.5 meters per second. So its speed is 11.5 meters per second when it hits the ground. Here is another example of projectile motion. In this case, our cannonball is fired at 20 meters per second at an angle of 60 degrees above the horizontal. So what we'll see is that its initial velocity has both a horizontal and a vertical component. But before we get to that, let's start, as we always do, by drawing a picture. In this case, it's fired over level ground, and the cannonball is going to follow a parabolic path. We assign an origin and a coordinate system. In this case, the origin is where it starts, and our x direction is to the right, and our y direction is up. Again, we should write down the kinematic variables, and this will have kinematic variables in both the x and in the y direction. So let's look at the x direction first. Its acceleration is 0 meters per second squared because, again, there is no acceleration in the horizontal direction because the acceleration is vertically downwards. To find the velocity in the x direction, well, this is really asking us for the x component of our original velocity. Let's draw a triangle to find this. We draw a triangle, and again, the angle is 60 degrees, and the magnitude of our velocity is 20 meters per second. To find the x velocity, we use our component formulas. In this case, v sub x is 20 times cosine 60 degrees, which is 10 meters per second. To find our y velocity, we apply 20 times sine of 60 degrees, and that comes out to 17.3 meters per second. Now that we have that information, let's enter it down. V naught in the x direction is 10 meters per second. X naught is 0 because it was originally located at the origin. For the y direction, a is negative 9.8 meters per second squared. The initial velocity is 17.3 meters per second, as we just found in our triangle. And the initial position in the y direction is 0 meters because it was originally located at the origin. So in part A, we're asked how long is it in the air? And the math question that corresponds to this is what is t when y equals 0? As you ask that question, you should notice that it will be at y equals 0 at 2 times. When it's first launched at time 0, and then when it hits again. What we'll see is the math captures this because it's a quadratic equation and it will have 2 solutions. One solution will be t equals 0, and one solution will be when it lands at the end. Well, let's start by writing down our equation. Again, we're going to use the first kinematic equation. We fill in our information, and then we simplify. As promised, you can see this is a quadratic with 2 terms. Both involve t. So I can factor out the t term. And now to solve this, I solve this by separating this into 2 separate equations. One equation is t equals 0, as promised, and the other equation will allow me to solve for the time in the air. I simplify that equation, and then I solve to find that the time in the air is 3.53 seconds. Like in the last problem, if you do this on your own and you get slightly different numbers due to rounding, that's not a problem. That happens. In part B, we're asked to find its range, and its range is defined as the horizontal distance it travels. So this is a horizontal problem, and the question we should be asking is about x, and in this case, what is x when t equals 3.53 seconds? We use the first kinematic equation, filling in our information, and solving to find that x is equal to 35.3 meters. So the cannon has a range of 35.3 meters. In part C, we will find the time it took to reach its maximum height. In the section on freefall, we studied the mathematical condition that guaranteed that an object was at maximum height. In this case, we need to realize that's only in the y direction. So the question here is, what is t when v sub y equals 0? You need to be careful that the total velocity in projectile motion will never be 0. It has no acceleration in the horizontal direction, and so its horizontal velocity will always be 10 meters per second and will not change. So the correct question is, what is t when v sub y equals 0? We use our second kinematic equation, fill in our information, and what we find is that the time is 1.76 seconds. Now maybe you realized a shortcut here, that if there is no air resistance, the time to max height is actually half the time in the air. That will not be true if there's air resistance, but when there is no air resistance, there is a nice symmetry here. It spends half its time going up and half its time going down. In part D, we're asked to find what is the maximum height it attains. And now that we found the time, it's just a matter of writing down the question, what is y when t equals 1.76 seconds? We use our first kinematic equation, plug in our values, and solve. In this case, we find that the maximum height it reaches is 15.3 meters. In part E, we're trying to find the speed when it hits the ground. And again, speed is the magnitude of velocity, so we're asked, what is the magnitude of the velocity when t equals 3.53 seconds? We'll need to find both the x velocity and the y velocity. Let's start by looking at the x velocity. In this case, v sub x is equal to 0 times 3.53 plus 10, and so you get 10 meters per second for its x velocity. This again makes sense because there is no acceleration in the horizontal direction. V sub y is equal to negative 9.8 times 3.53 plus 17.3, and what we get is negative 17.3 meters per second. Because it spends the same amount of time on the way up as it does on the way down, this is what we would expect, that its initial velocity when it's launched is the negative of the velocity when it hits the ground. We now solve for the speed by using the Pythagorean theorem, and the value we get is 20 meters per second, which is again the speed with which it was launched. This just goes back to the same symmetry we've been discussing before. And so its speed is 20 meters per second when it hits the ground.